Okay, so today we have Noemi talking to us remotely on her recent work, efficient registration-based encryptions. So please take it away.
All right. Yeah, thank you for the introduction. Thanks so much for having me. I'm sorry I couldn't be here or there in person, but I'm still excited to share this work with you. This will appear at CCS this year, and is joint work with Dimitris Kolonelos, Giulio Malavalta, and Amadreza Rahimi. Some things will kind of build on each other, so please just stop me if you have questions, and I can answer them during the talk. Okay, so the motivation behind this work broadly is secure communication. So if we have two parties, Alice and this dodo, trying to communicate with each other, but worried about some eavesdropper reading the messages they send, we can solve this pretty easily with decades-old cryptography, namely, in this case, public key cryptography. So if Alice has the dodo's public key, she can use it to encrypt her message, and now an eavesdropper won't be able to read it. There is still kind of this issue of how does Alice learn the dodo's public key? This is also sort of solved. So one simple case is something kind of like a LAN party, where if they meet each other in person, the dodo can like physically hand over a copy of his key to Alice, and then she's sure that the key actually came from the dodo when she uses it to encrypt her message. And Signal kind of approximates this too, in like a modern day example, where if you actually are physically close to somebody you have on Signal, you can verify each other's public keys and make sure that you're actually using the public key that they think they're giving you. A more practical scenario is if we're not going to be physically in proximity, usually we just kind of delegate some third party that we trust. So in this case, Signal, maybe some certificate authority, and we ask them to provide the public key for us and just trust that they are going to be honest about whose public key that is. So this is known as a public key infrastructure. The trusted party in this case is the certificate authority, and they maintain this directory of identities and public keys that they've put their stamps of approvals on. So that's this little icon there. And the flow generally is that if a user wants to join the system, they generate their own key pair, and then they send their identity, the public key, and some kind of proof that they are who they claim they are to the certificate authority, who will verify that they are actually that identity, and then store this ID public key pairing that they've certified in their directory. Now, if somebody wants to send a message to that identity, they can ask the certificate authority for the corresponding public key. And then we proceed as normal, where they can just use the public key with whatever their favorite public key encryption system is to generate a ciphertext and send that to their the dodo. Okay, this is pretty standard stuff. In practice, actually, though, PKIs can be pretty error-prone to implement. We have kind of this whole complex web of trust that's been developed of like multi-layered certificate authorities that we kind of implicitly trust at some point, some kind of central root. And in the 80s, Shamir asked if there's kind of a way to avoid all of this extra machinery that can lead to a lot of problems. And he suggested maybe we can actually encrypt directly to the identity string itself, some unique string that identifies a party, so like their phone number, their social security number, email. And this is called identity-based encryption. So in this case, registration is pretty simple for the user. They actually don't generate their own key at all. They just go to the key generator with their identity, and again, like their license or something, and they say, hey, I'd like to join the system. The key generator is this trusted party who has a master key pair, MPK, MSK. And when some party wants to register with them, they use their master secret key and the identity to derive some identity secret key, SK. And that's what they send back to the user. Now, if a sender wants to send somebody a message, they can just use the identity that they know of like who they're trying to communicate with directly, along with this master public key, which is just posted online somewhere, and generate the ciphertext basically non-interactively, and then send that to the user who uses their secret key, which again, they have locally to just decrypt the message. Are there any questions about this flow? Okay. All right, so this looks pretty nice. Unfortunately, there is still this master secret key here, which can be a big potential threat. So anyone who has that master secret key, whether it's the key generator, or if they accidentally lose it, their system is not that secure. If somebody is able to exfiltrate it, some adversary, they can recompute or compute a fresh secret key for any party, one who's in the system or even one who never wanted to join the system, and decrypt any ciphertexts that were intended for that party. And then a malicious key generator could also maybe generate the secret keys it issues in some faulty, constrained way. So maybe they don't want people sending some kind of messages, so they make the secret key in a way that it fails to decrypt messages with banned words in them. So the natural next question is it possible to get this nice, convenient property of encrypting directly to an identity string while also avoiding this extremely strong trusted third party? And in 2018, Sanjam Garg and others introduced this new primitive called registration-based encryption, which aims to do exactly that. So this is kind of, you can view it as an in-between between a PKI and IBE. Again, the user is going to generate its own key pair now, like back in the PKI setting, and it's going to send the identity, public key, and proof to this key curator. This key curator is, again, still a third party. It's a central party, but it's completely transparent. So it's just going to kind of accumulate public information, similarly to how the certificate authorities do. But it's completely transparent, and all the information is public, so there's no secrets like the MSK. Then when somebody wants to send a message, they use this public parameter, PP, that the key curator has been updating, the identity and the message, and send that ciphertext to the user. And again, the user can use its secret key, which it generated locally and only it knows, to decrypt the message. Now, because the key curator is updating as like the system parameters as parties join, the user might need some kind of updated auxiliary information every once in a while to make sure that it can decrypt messages it's sent that were generated using older parameters. Are there any questions? Yeah.
Yeah, so is it necessary that the initial public parameters is generated using an MPC? Like, can we have like a transparent setup?
Yeah, actually, it depends on the construction. So I probably should have removed that part from the slide, because the GHMR constructions, I believe they have the setup basically outputs empty strings, so it's no setup. The construction that is in our paper that I'm going to introduce, that one does use a kind of trusted setup, but it's not inherent to RBE.
Okay, thanks.
Yeah.
Question. So the key curator is transparent. So does that mean everyone can see the information, but it is semi-honest? So all the evaluation is like it's done honestly.
Yeah, we assume that it is actually running this registration like update honestly. Since if we imagine this, like all of these registrations being posted on a bulletin board, anybody could kind of, recompute what the update should be and call out a malicious key curator if they don't do it correctly. But I suppose if in the absence of kind of like this public log, then it is just a semi-honest setting. I will talk later. There's an extension that introduces verifiability to like basically audit a potentially malicious key curator, and that kind of helps solve that problem.
I see.
Okay. Right. So the flow here is pretty similar to the PKI. And in fact, you could trivially instantiate RBE with a PKI if you just kind of make this public parameter concatenation of all the keys of the registered parties. So we have some compactness and efficiency requirements for RBE. So first of all, we want the public parameters to be sublinear in the number of users, or specifically polylogarithmic. And then we want registration and obtaining of updates to be fast in some sense. I'm not going to define this very rigorously, but just to avoid kind of the trivial construction. And we also want a party to not have to get updates every time a user registers in the system. It should be more infrequent. Okay. So then we also have some kind of standard cryptographic properties of RBE. So for completeness, this is kind of a correctness sort of property. If everyone behaves honestly, even if some malicious parties register in between, then still encryption and decryption to a particular honest party should function as expected. And then for security, we have a CPA-like security notion, which later I'll show that you can update it to CCA security using the FO transform. And as somebody mentioned earlier, we might want this additional verifiability property. This is from a paper by Vipul and I don't remember the second co-author. But basically, in case we're worried about a malicious key curator, we can add proofs of membership or non-membership. So parties can audit the key curator and make sure that they were actually registered when they were supposed to be registered, or that the key curator hasn't secretly registered them when they didn't want to be registered. Are there any questions? Okay. So I think next I'm showing a construction from IO. This is kind of the feasibility construction from the original RBE paper. They also give a second construction, which is based on more standard primitives, but it's weakly efficient, so it doesn't quite meet the full efficiency guarantees that I explained earlier. And the outline is kind of similar. So I want to show you this just so you know that, like, how RBE has been constructed until now and why this new construction is actually practically efficient and how it's different. So the public parameters in the IO construction are simply a Merkle tree of all the parties that are registered. So when a new party registers, we're going to add them to the leaves of the tree, and that updates the root of the tree. And we're actually going to have a forest of trees. So at this point, the tree is full. If another party registers, we're going to start a new tree over here. And our public parameters are going to be the roots of all the trees. And this helps make the updates less frequent, because if you're in this first tree, you don't really need new information. Oops. If other parties have registered, but they're in like other trees, it doesn't matter. As far as you're concerned, you don't need this update information. Okay, so back to this kind of simple case where we just have one tree. For encryption, our ciphertext is going to be an obfuscated program. So this is the program. It has the public parameter, so the root of the tree, hard-coded in. And we also hard-code the identity and the message. And the way the program works is it takes as input this copath. So this yellow, these yellow elements I've highlighted in the tree. And if you provide a copath that is consistent with the identity and the root, this program will output a ciphertext. And otherwise, it outputs bot. And we're going to obfuscate this program. So again, public parameter and ID are hard-coded. Input is a copath, and the output is either ciphertext or bot. Does this make sense?
So does the input to this program also has M, like the message as another input?
The message is actually also hard-coded, so I think maybe I should update my slides and include that here in this like white box. It's obfuscated inside the program. Because remember that this obfuscated program as a whole is going to be like this black box is what we'll send to the recipient. They don't know the message. They're trying to learn the message, right? So they just get this black box.
I see.
Yeah.
Okay.
Okay. Right. So
A question?
now, yeah.
So how does the sender know PK?
PK. Oh, actually, I guess I think I made a mistake, and PK should also be an input then.
Or
so the top the input we have 4 inputs: PP, PK, ID, and M.
Yeah. So the you can think of the program as basically like the purpose it serves is just if you're the proper identity. Oh, actually, the public key is kind of part of the copath. So I suppose I should highlight that. So you can think of it also, yeah, again, as an input. So the program is basically enforcing that it will only output the ciphertext if you are that identity. Like it just outputs the ciphertext for a particular identity at a particular path. The public key and the ID are kind of bound together by this path, by their position in the tree. So there's no way an adversary can kind of like trick this program into outputting an encryption under a different public key, because that's just not how the tree is made.
But now I have a question here: isn't that the benefit of using RBE rather than PKI is that the sender doesn't need to know PK?
Yeah, so the sender doesn't know PK when they're creating this program. This copath, that's kind of like a free variable when they're creating this program. That's what's going to be input by the recipient.
So when you decrypt, the decryptor will input kind of their path, and that'll retrieve a ciphertext encrypted under their key.
Exactly, yes.
Okay.
Okay, so in this case, the ciphertext is actually the ciphertext that the sender generates is actually the IO program.
Exactly, yeah.
Not
this black box is the ciphertext. So there's kind of like ciphertext at 2 levels, right? There's like the RBE ciphertext is this black box, and the decryptor will get the black box, input the copath, and it will get out this, lower level ciphertext, I guess, which is an encryption under its public key.
I see.
Those were good questions. I was wondering the same thing. Yeah, that's a good answer.
Yeah, thank you.
Yeah, okay. Yeah, I think this can be kind of like hard to wrap your head around the first time, because like ciphertext is kind of overloaded. So yeah. Okay. Yeah, I'm gonna go through decryption next too, so that'll kind of like hopefully help solidify that. So the user receives this black box. It might have some outdated information about the copath. So maybe, this figure on the right, this tree is the way the parameters looked at the time of the ciphertext generation. It might be that the recipient only got the copath like several registrations ago, so it's an outdated path. So what it needs to do first is potentially get an updated copath. So this is this update algorithm over here. And it gets that A from the key curator. I'm going to call it A for like auxiliary information. And now it has its secret key and this black box. It can update, it can input this new path, and this black box will spit out the ciphertext. And then it can use its secret key to recover the message. So this is what we were saying earlier. Does this still make sense?
Okay, question. So what if the sender used the old information, the old PP to encrypt it? And when a user wants to decrypt it, the user asks the curator to get a newer version, which is PP prime.
Yeah, so it basically has to use the copath at the time that the ciphertext was created. Or maybe, I mean, I guess there's some leeway, right? If the particular subtree wasn't updated by some registrations, it doesn't really matter. But if it tries to use a new copath that's different, actually, sorry, you're right. I think somebody objected because the copath does change. If it tries to use an old copath, though, the box will output bot, and it knows that that's not correct, and it basically will use its older version of the path. Like it'll have to use a previous version. It doesn't always need to use the most recent one that it gets from the key curator.
So that means the curator has to save all the history of the tree.
Either the curator or the user does. So the user has to basically ask for updates at the right intervals, or somebody has to maintain a history.
Yeah, because we don't know when the ciphertext is generated. We'll have to use the correct version.
Yeah.
Okay.
Like output the M, like if you were to verify that like SK corresponds to the correct public key, like inside the obfuscation.
Wait, I missed the beginning of the question.
In that case, the key curator would be able to also decrypt. So the trick is the key curator knows the path, but it doesn't know the secret key that corresponds to the public key. So the key curator can also pull a ciphertext under that public key out of the obfuscated program. But even if it gets that, it still can't decrypt because it doesn't have the secret key.
Oh, I see. Okay.
Yeah.
If I compare to the PKI is actually easier to the user because the user can just use its secret key to decrypt. But for the RBE, there is an overhead for the user because user need to ask the auxiliary input. Auxiliary information.
Yeah.
And information has to be like consistent with the ciphertext.
Yeah, so there's definitely, I think it's a really rich space of trade-offs. There's a ton of different dimensions to consider between like comparing PKI, IBE, and RBE. There's like having to deal with updates, but you might optimize for the decryptor versus the encryptor, or how anonymous the system is, because here, the public parameter a user, the encryptor uses, like the sender, this public parameter is completely independent of the recipient. So the key curator, just from their queries, doesn't learn who they're trying to send a message to. So there is kind of like also this anonymity point. There's a ton of different dimensions. So one of them, yes, I guess ease of use is lower in this setting compared to a PKI, but in a PKI you might have less anonymity.
I see.
Yeah. So yeah, this is the construction that was introduced in the paper that introduced RBE. Like I mentioned, they also have another construction that is from more standard assumptions than IO. It's still kind of this tree-based idea, and they basically traverse the tree using nested garbled circuits. So it's not much more efficient. And that's kind of every construction so far until this work in the literature was using this sort of paradigm. So in this paper, we give the first practically efficient RBE construction. As I mentioned earlier, we do have to use a trusted setup, so we rely on a common reference string, and our construction is pairing based. So just a very quick refresher on pairings. A pairing is a bilinear map. It takes 2 inputs, 1 output, and it follows these properties here. So if you have exponents inside the pairing, you can move them between the coordinates or outside the pairing. And if you have a product within a pairing, you can kind of split these elements into 2 separate pairings as long as 1 coordinate is constant. Okay. So I'll dive into our construction unless there are any questions. Okay, right. So the idea with our construction is to basically group users into buckets. So I'm going to use big N for the number of users in the system, B for the number of buckets, and then N over B is the number of users that will fall into each bucket. And I'm going to go through a toy example. So I'm going to have use identity 7, which if the bucket size is 4, that's going to be the third identity in a bucket. Okay. So the CRS is going to be a powers of tau CRS. If that doesn't mean anything to you, that's fine. It's basically the length of the bucket size, but actually double that and puncture out one of the elements. Right, and you can generate this using kind of a decentralized iterative ceremony where you just have to trust yourself. So people can contribute randomness sequentially, and that kind of, I think to me at least, that means that the trust assumption is really quite minimal. Okay, so in our construction, the key curator is going to maintain this public parameter and auxiliary information. So the public parameter is just, there's one element per bucket, and it's going to accumulate parties' public keys. So you can think of each bucket as a commitment to all the public keys in that bucket. And then you can think of the auxiliary information as like every party has its, in a bucket has its own aux element, which is sort of a decommitment, an opening of the bucket to all of the public keys except that party. So it sounds a bit convoluted, but I think it'll be more clear than the construction when we go through the construction. But kind of like, in summary, buckets are commitments to the keys in that bucket, and everyone has their own opening for a bucket. Okay, so to register, a user needs the CRS. And we're going to assume one limitation of our program, or sorry, of our construction is also that we assume the identities are ordered. There's like a public mapping from the identity space to the range 1 to n. I'll talk a little bit at the end about a work that kind of circumvents that. But for now, that's one of the limitations that's kind of inherent in our construction. So again, every party is going to generate their own key pair. You sample a random secret key, SK, and then we're going to actually use a CRS element raised to the SK as our public key. So for party 7, it's the third party in its bucket, so it's going to use the third CRS element raised to its SK. And then we also compute some helping values, which I'll call this vector A. And that's an n over b size vector. It's all the elements right after my position in the CRS, this blue spot. I'm going to take n over b elements after that, raise them to the SK as well.
Do you multiply the elements?
This is a vector, so there's going to be
okay.
that number of elements in the vector.
Oh.
And now to register, I send my ID, my PK, and that vector. The key curator is going to run some pairing checks, which essentially are just checking whether the secret key that I used for the public key is the same as the secret key I used for each of the elements of that vector. And if that check passes, it's going to register the party. So we're going to multiply the public key into our bucket. So this bucket is just a product of public keys. And then we update the auxiliary information with like quote unquote decommitments. So we put our vector A here, multiply by each element that was already an aux to get some new vector, and we append that to our aux. So our auxiliary information is kind of like a matrix. Okay. Again, kind of a lot of setup, but I think hopefully it'll make sense why we need all these things when I go through encryption and decryption. So for encrypting, I need the public parameters. Actually, I only need really the bucket for the user I'm encrypting to. So there's kind of a built-in sort of storage usability versus privacy trade-off or anonymity. So I can, take all the buckets so that I don't leak which bucket I'm interested in, or I can just ask for a single bucket. So that's one element of our ciphertext. Then we also have a pairing between that product of public keys and a CRS element that depends on the identity, raised to some randomness. We also include G to the R as like a commitment to the randomness. And then this last element is like really the important part. So we use these CRS elements raised to the R to mask our message M. Okay, and now hopefully for the part that clarifies everything, here's the decryption algorithm. So I need my auxiliary information, which again, every party has their own list. So for the identity, they get their own column here. And we basically, as we were saying with the tree construction too, you need to use the information from the time the ciphertext was created. So naively, you could try all of them and see which one works. In our case, there's also a nice pairing equation you can check to see if your element is the correct one. So you just find this opening H where this particular equation holds. The details aren't as important. I'm basically going to simplify for you what the important part is. So this first ciphertext element, this bucket here, we're going to use that to basically check whether our opening is the correct one. So remember, this CT1 is the public parameters for the bucket, which is just a product of public keys. This blue public key is the identity's public key. So because of the properties of pairings, these public keys cancel. So we're left with the singular pairing. Right, and I'm going to use this fact later that H is an element such that this equation holds. Any questions? There's still, I'll go through the decryption algorithm next, but before that.
Quick question, what is G here again?
Oh, G is just a generator.
Oh.
Public, yeah. Okay, so let's keep this fact in our back pocket and we'll use it during decryption. So we used the first element of the ciphertext CT1 already to find H. Now we're going to use the rest of them and extract the message back out. So this is our decryption equation. If I'll like step by step expand things out. So the CT3 was defined as G to the R. Remember, oh, right. Yeah, we can move this little R, the exponent, out of the pairing because of the pairing properties. And now remember that we said that fact holds about H. So this pairing here is actually equal to this other pairing right here. That's just because H is the correct opening. So, okay, so now let's expand this CT2 element. That looked like this. That's how we defined it in our ciphertext. So you see some stuff actually cancels here. So these public keys cancel. We're left with just the identity's public key. And these pairings look pretty similar. So we can combine like this. And now let's expand out CT4. Oh, wait, no, never mind. Let's expand the PK first. So remember the party, we define the public key as the CRS element raised to the SK. Now we cancel the secret keys. Okay, and now we can expand CT4, which conveniently looks exactly like that. And we can cancel to recover the message. So at a high level, what's happening is that we have an encoding of the randomness. We have this opening to all the public keys except our own public key, which was the aux information. And so we can use that to basically cancel all the public keys except our own, and then use our secret key to recover the message. That's the intuition. The math with pairings always gets kind of messy. Are there any questions? Okay, that's as technical as I'll get. I think now we can kind of zoom back out. So that was our basic construction. I'll show in a minute how the performance is. We actually implemented it. We also give an extension that has more efficient updates. So there's fewer updates, and I think there's just fewer updates. And the basic intuition for that is, instead of having a single public parameter, we run logarithmically many copies in parallel. And so say we have 2 parties registered in this bucket. If another party registers, we'll create a second parallel copy of public parameters. And this increases our ciphertext size. So we have to encrypt with respect to every copy of the public parameters. And then if another party registers, now we have the same number of parties registered in these 2 buckets, so we can run a merge. So we just multiply their keys together and put them all in one bucket. And this means that the updates are less frequent, because you basically only need to update your decommitment information when a merge happens, because that's the only time your bucket will be updated. Okay, so the bottom 2 rows are our construction. You can see it's less asymptotically, it's not optimal compared to the previous constructions, which were logarithmic. The square root comes from, we basically set the number of buckets to the optimal setting, which is square root n. So you have square root n buckets with square root n parties. So yeah, basically we sacrifice this asymptotic efficiency for practical efficiency. So these are our runtimes. I think even run on a Mac, actually. We use Python wrapper around relic, and we implemented this with an asymmetric pairings. So the setup can be kind of expensive, and registration, those 2 are kind of the most expensive things, but those are, one time for the whole system or one time per user. And they're still just on the order of seconds, but encryption and decryption are really fast, sub 1 second, or, just on the order of like microseconds.
So I have a question. The auxiliary information, is it for every client or like total? For
No,
all?
this is total.
Okay.
Yeah.
So
yeah.
Yeah, I guess like per client, how large would it be?
I guess it depends. So it'd be basically like this number here for aux divided by the number of users, roughly. It kind of, this is like, I think this is in the worst case, when like everyone is registered, but kind of depending on what buckets people register in, it'll be distributed differently over the course of the system.
Okay.
Yeah, so this, you're right to focus on this, because aux is basically the limiting factor here. It's the biggest amount of storage. I still think it's reasonable. You can like go buy a hard drive now with 2 terabytes of storage. It's not great, but it's still possible, and that's for 10 million users. So, if you
So
have...
this is like the key curator, right? That's the only party that needs to hold this 1.9 terabyte.
Yeah, exactly.
Okay.
Okay. So that's kind of the basic stuff. I have a little bit about extensions to kind of add some more features to our basic construction. but maybe I'll pause for a second and take some more questions first, if there are any. Okay, let's get into some extensions then. Right, so as we've mentioned, this is kind of assuming the key curator is just semi-honest. It'll actually perform all these updates correctly and register people correctly. We basically get membership proofs out of the box because this last element of the auxiliary information, so the most up-to-date aux information, is in itself already a proof of membership or non-membership. You can just do a single pairing equality test to check whether you're registered or not registered, as you should be. So by you, I mean your public key. So remember this bucket, it contains all the public keys. Maybe your key is in it, maybe your key is not in it. And so you can check this aux information, which basically decommits to all the public keys in a bucket except for yours. And if your key is supposed to be in it, then this top equation should hold. If your key shouldn't be in it, then this bottom equation should hold, and you can check whether you've been registered or not. So I think it's pretty neat that we just get that out of the box, basically. As I mentioned earlier, you can also get CCA security, again, kind of modularly for free by just applying the FO transform. And then we also show how to enhance the anonymity of our scheme. Right now, some of the parts of the ciphertext leak some information. Mostly they leak which bucket the recipient is in. So if you want to hide that, we show that, like how to hide that, basically at the cost of doubling the size of your ciphertext. So the way to do that is, instead of having this public parameter for your bucket as the first element of the ciphertext, what we can do, remember that CT1 was used to check whether the update information you're using to decrypt is the correct one. So what we can do instead is we can basically have two parallel encryptions. So an encryption of our actual message, and then an encryption of some randomness, and a commitment of the message, to the message with that randomness. So then we kind of just try to use an update to decrypt both of these ciphertexts. And if we get an opening, this randomness O, which is consistent with a message, like if the opening works properly, then we've used the correct update information and we're able to decrypt. Otherwise, something will go wrong and we have to use a different update. Okay. That's basically everything I have. I have like a few open questions listed on this slide for some limitations and whether they've been overcome or not. And yeah, I think I welcome you to check out the paper on ePrint. I think it's pretty up to date. And also, if you're going to CCS, you should attend the talk. Yeah. I won't be giving it, my co-author will, so you might get something different out of it.
Thanks.
Yeah, thank you.
So yeah, I guess my question would be like, what is this attribute-based RBE? How do you define it?
Right, so attribute-based encryption is kind of like a generalization of identity-based encryption. So instead of encrypting, this is what I covered at the beginning of the slides, this thing by Shamir. So instead of encrypting to some identity string, I can define a set of attributes. So maybe like student, like in computer science or something like that, and encrypt a message to a set of attributes. And then anybody who holds those attributes can decrypt the message. So yeah, it's a generalization because I guess you can think of identities as like an attribute where the number of members in the attribute is like 1.
I see. And is the scheme in that paper efficient or not?
So they argue it's efficient. It's it's a bit hard to, we actually got this comment in a submission, and so we have, if you're interested, I can also like send you kind of what we wrote as a rebuttal. They don't really implement their scheme, so the paper doesn't have an implementation, and it's kind of, they get it through a transformation to some kind of like more basic scheme. And there's, if we're trying to kind of map that onto the RBE setting, it's hard to compare because it's kind of apples to oranges. I think it's, again, it's hard to say. I think in our rebuttal, we said that making some kind of conservative estimates that were like favorable to them, our scheme is still more efficient. But their scheme is definitely more efficient than this like IO based stuff that came before it.
I see. But is it based on bilinear maps or LWE or what?
I have to check. I want to say it was lattice based, but I might be remembering wrong.
Any other?
Do you know how this follow-up work like resolves the ID not being restricted?
Yeah. So they basically, you can think of our scheme as kind of so I don't remember the details exactly, but they basically use something kind of like updatable commitments. So in our case, you can think of the public parameters as like a commitment to public keys that are in like a specific order. So you kind of have to know where they are in the order. They use cuckoo hashing combined with like an updatable commitment scheme, so they can kind of hash to a position and then like move that position around in the commitments very loosely at a very high level. But I think it's kind of plug and play, so you can kind of just like take what they did and like map it on top of our scheme.
See.
Okay, thanks.
Yeah.
Another question I have, like with this applications, do you have, like in your mind, do you think there's a compelling application here for this, for your scheme?
So I think the obvious one is like I write as like a transparent drop-in or a drop-in for PKI that's more transparent. Again, there's a lot of trade-offs in the space. That's the more obvious application. I think there might be other applications if you kind of like interpret this more loosely as like a type of paradigm for laconic cryptography more generally. I didn't talk about that in the slides, but I'm happy to talk offline about that. Yeah, I think one of the professors at UMD is convinced that there's like great applications for this, but you have to like think outside the box, and I'm happy to hear about anything that you think makes sense where you know, you could apply this to something that isn't as obvious as a PKI.
Cool. Yeah, any other questions? Great. Let's thank the speaker again.
Thanks so much for having me.